Determination of optic sign involves use of the plate to determine whether E or E' is fast or slow. To do this, we need to understand the directions in the interference figure. Here's a typical uniaxial centered optic axis figure. The optic axis is at the intersection of the extinction bands called isogyres and is shown by the blue spot. Unlike a normal image, vibration directions vary from place to place in the field of view. Here the E' vibration directions are radial, and only 4 of them are shown. O vibration directions are normal to the E' vibration directions. The isogyres do not rotate when the stage is rotated. To determine optic sign, we need to determine if E' is slow, optically positive, or fast, optically negative. In effect, we compare the northeast-southwest vibration directions in each quadrant of the figure with the slow of the plate, marked S. Here's the effect of the plate. Plate in. Plate out. Plate in. Note how the compensation effects are opposite in adjacent quadrants, but the same in opposite quadrants. This is useful for comparing rises and falls. This shows why the compensation effects change across an isogyre. E' vibrates parallel to the slow in the plate in the northeast quadrant, but O vibrates in this direction in the adjoining quadrants. The northeast quadrant shows a fall, so E' must be fast. Alternatively, we could reason that the rise in the adjacent quadrants must mean that O is slow. Both approaches lead to epsilon less than omega, that is, optically negative. Here's one for you to try. Plate in. Plate out. Plate in, and there's a rise in the northeast quadrant. Therefore, E is slow and the mineral is optically positive. Here's another figure for you to try. Plate in, plate out. Plate in again, and you can see when the plate is in as the isogyres go purple and the symmetry is reduced. Concentrate on the northeast quadrant. There's a rise in the northeast quadrant, therefore E' is slow, therefore optically positive. Try this one too. Plate in, plate out. Plate in. Note how the first order red shows the most obvious shift to black for a fall and to second order red for a rise. There's a rise in the northeast, so E' is slow, therefore optically positive. So far, the uniaxial figures have been centred, that is, the optic axis or C-axis vertical. Off-centred figures are more common. In slightly off-centred figures, the optic axis may remain inside the field of view, so sign determination is easy. In more off-centred figures, the centre of the cross is outside the field of view, so quadrant recognition may be more difficult. Here's a centred optic axis figure, and I'm tilting the crystal slightly so the optic axis moves from the vertical. Rotating the stage causes the centre of the isogyre cross to rotate in the same direction. The isogyres do not rotate. Another demonstration of off-centred figures uses a glass bead held over the grain under low power. This is a centred optic axis figure, and here's the effect of twisting the C-axis of the grain from the vertical one way, then the other. Now I'm tilting the grain again and rotating the stage. Here's a conventional, slightly off-centred figure. The isogyres remain east-west and north-south during stage rotation. Try to keep track of where the centre of the cross is during rotation. Determination of optic sign is easy as the quadrants are easy to recognise. Here there's a fall in the northeast, therefore optically negative. Strongly off-centred figures show only a single isogyre and resemble biaxial figures. Recognition of the quadrants, a prerequisite for sign determination, may be more difficult. Here, the optic axis is outside the field, either to the north or to the south along this isogyre. Here's a good rule to use to solve this problem. Slight clockwise rotation of the stage results in this new position for the isogyre. The two ends of the isogyre have moved round the edge of the field of view in opposite directions. The end that rotates the same way as the stage is rotated is nearest the optic axis. Here, the southern end rotates clockwise, so the optic axis is in the direction of the yellow arrow, and the main quadrant visible is the northeast quadrant. Here the stage is rotated anti-clockwise, and now clockwise again. The rule to locate the optic axis works in each case. I'll continue this clockwise rotation. Another method to locate a particular quadrant is to frame it by clockwise and anti-clockwise rotation, as here. This is the northeast quadrant, and the fall means optically negative, and the southeast quadrant shows a rise. Presence of isochromes makes it easy to locate the optic axis, as they are concentric about it. This is the southeast quadrant, and that's the northeast quadrant. And the rise in the northeast means positive sign. And going to the southeast quadrant, the fall also means positive sign. If the optic axis is too far outside the field of view, the isogyre may be fuzzy and bend slightly as it sweeps across, as in some biaxial figures. This is the northeast quadrant, and the rise there shows the figure is positive. And rotating to the southeast quadrant, there's a fall. Flash figures result from maximum interference colour grains. That is, the optic axis parallel to the stage. A diffuse cross rapidly breaks into isogyres which leave the field from opposite quadrants, like a biaxial figure. Here I'm oscillating the stage about the diffuse cross position. It's best to choose grains giving slightly off-centred figures like this one. Sign determination is simplified, and the distinction between uniaxial and biaxial figures is much easier. This mineral is optically negative. Fall in the northeast, a rise in the southeast quadrants. Selecting the right grain is crucial to getting a useful interference figure. The interference colour of the grain must be very dark first order grey, or if the birefringence is low, black. Rotate the stage for each field to see the interference colours of grains at extinction. There's no suitable grain here. One grain near the edge of this field does remain black. That is, the optic axis must be nearly vertical. Shift this grain to the crosswire intersection, increase magnification, and check that the grain remains centred during rotation. Then swing in the auxiliary condenser if one is fitted to the microscope, open the diaphragm and use the Bertrand lens to get a figure.